In this video guide, we'll be looking at some rotational equilibrium problems where we're dealing with an angle. And for all torque questions, it's important to note that a torque is a vector, and a torque is kind of like a twisting force being applied to an object, and all torques are perpendicular to the direction in which the force is being applied. So these kind of concepts were probably mentioned in your class notes, and now let's go ahead and apply them to a few of these problems. Alright, so for this very first question, we have a uniform 45 kilogram beam of length 3 meters. So this whole length right here is 3 meters, and its mass is 45 kilograms. Okay, and we have an angle of 53 degrees right there, and our goal is to find the tension in the cable. So the tension in the cable is denoted by this green color right there. So there's a force in that particular cable, and we need to calculate it. Okay, so for most of these rotational equilibrium problems, it's a very good idea to find a pivot point, because once you find the pivot point, your torques will be referenced around that pivot point. So a very good strategy is always to put your pivot point at the very end of one of the beams there. So I like to put it right against the wall there. After that, you want to find all the forces acting on this particular beam. So let's call it the free body diagram. Okay, so since the beam has a mass of 45 kilograms, it has a center of gravity right in the middle of the beam. So here's your force of gravity acting in the downwards direction. So that's your first force acting on this particular problem. And since we have a cable in this particular problem where we need to calculate the tension, we also have a force tension right here. So I can label that as F with a subscript of T. So there's our free body diagram for this particular problem. Okay, so as mentioned before I started this particular problem, when we're dealing with torques, we always have to work with the perpendicular forces that are acting on the object here, right? So if I look at my first force, my FG there, it's definitely perpendicular to the pivot point, so that has no problems there. But this force right here, the tension in the cable there, since it's going off at an angle there, it actually creates two components. So one force in the horizontal direction and one force in the vertical direction. Now, we're not really concerned with the force in the horizontal direction, but the force in the vertical direction, this is actually perpendicular to the pivot. So we want to find an expression for the force in the vertical direction there. So we know this is 53 degrees, we know this is 90 degrees, and we know all angles in a triangle add up to 180 degrees. So you can definitely find this angle to be 37 degrees. Now, this is very similar to projectile theory. So when you have a kind of a number there that's going off at an angle, you can always find the vertical component of that by taking that number, which in this case will be the force tension, and you multiply by sine of the angle, so sine of 37 degrees. All right, so that right there is your perpendicular force with respect to the pivot there. Okay, so once we do that, it's important to know where the torques will be calculated. So usually the torques will happen when you have a force acting on the object here. So right here we'll have a torque here, so I'll call that torque 1, and this is the other perpendicular force, I'll call that torque 2. So those are the torques that we will be needing to calculate in order to find the force in the rope in this particular problem here. And then now that once we've dealt with all the forces here, we want to go ahead and set the concept for rotational equilibrium, and that means the sum of the torques equals to 0. Okay, so let's go ahead and start breaking down this problem here. So at the pivot point, in order for this beam to not move, we want to say that the sum of the torques is equal to 0. And that literally means that the sum of the torques in the clockwise direction is equal to all the torques in the counterclockwise direction. All right, and that will ensure us that the beam is not moving, and that will establish rotational equilibrium. Okay, so what does this all really mean? So let's go ahead and draw another diagram right here. So I'll just draw a horizontal, not that one there. I will draw a horizontal line right here. And just remember that this point right here was our pivot, and we had a torque going in this direction. I'll call this torque 1. And we also had a torque in that direction. I'll call that torque 2. And that was really like the force in the vertical direction there, right? So those are all the perpendicular torques here. or the forces acting on that particular beam there. And with respect to the pivot, I want to say this first torque is kind of going in this direction, right? So this is in the clockwise direction. And this second torque with respect to the pivot, this is going in the counterclockwise direction. Okay, so in the clockwise direction, we just have the one torque here, so I'll label this as T1 or torque 1, and in the counterclockwise direction we have one torque, which is torque 2. Okay, now the general formula for a torque is really the force times the distance, and the general formula for torque is force times the distance. Now in this particular case, this force is really the force of gravity. And let's just go ahead and figure out what this distance here is. What is this distance of this first torque? And that is denoted by this distance right here. Okay, if I go back to the original problem, I know that this entire length right here is 3 meters. So the force of gravity is always halfway between, is the halfway distance. So this will be 1.5 meters. Okay, so on my diagram here, let me label this as 1.5 meters. And I'll go ahead and plug that in for my distance there. So that first torque is 1.5 meters from the pivot point. Okay, now what about this second force here? Well, that second force is really that force that's acting in the vertical direction, and we denoted that was going to be the force, this force tension, times sine of 37 degrees. All right, so that is the perpendicular force right there. So let's go ahead and plug that in. This is going to be your force tension times sine of 37 degrees. And this actual distance, this entire green distance here is actually 3 meters from the pivot point, right? So let me just times this by 3 meters. Okay. So that's looking pretty good there. So let's go ahead and figure out what Fg is. Well, Fg is the mass times the acceleration due to gravity. So the mass of the beam here was 45 kilograms. So this will be 45 times 9.80, right? So mass times the acceleration due to gravity times the 1.5 meters. And that's going to equal to the force tension, which we need to figure out. And then sine 37 is just a number, so sine of 37 degrees, and then we multiply that by 3 meters. All right, so we have enough information now to find your force tension there. So now you're off to your calculator here. So if I multiply these three numbers here, I'll get 661.5. And on the right hand side I get force tension, and if I multiply these numbers together I will get 1.8054, and then you can now find force tension by taking the 661.5 and dividing that by 1.8054, and you'll get roughly 366.39. And if you round that to two significant figures, that's going to be 370 newtons. All right, so either one of these answers is a suitable correct answer for this particular problem. Okay, so let's go back to the problem now. Let's just erase all the colors here, and let's just, once again, what we found was the tension in the rope here, and that tension is roughly 370 newtons. Right? So if the tension is 370 newtons, then that will keep the beam in rotational equilibrium, meaning that nothing is moving. It's at rest as it is. Okay, so that's the solution for that first particular problem. Here is the second rotational equilibrium problem, and once again, just remember a torque is a vector. It's like a twisting force being applied to an object, and the torque is always perpendicular to the direction in which the force is being applied. All right, so let's go ahead and put those concepts into practice now into this particular problem here. So there's a lot going on here. So we have a hungry 8-kilogram raccoon, and it's walking out on this uniform beam, and the beam is 2 kilograms and it's 2.2 meters long. And the raccoon is trying to reach the 1.3 kilogram food basket hanging at the end. And we also have a cord that can withstand 91 newtons just to support the beam. So right now in this diagram, it's in rotational equilibrium. So that means everything is not moving. However, if the raccoon keeps on walking further to the right-hand side, then the beam will break. So we want to find out what is the maximum distance that this raccoon can move to the right so that the beam is still in place. Okay, so step number one for this rotational equilibrium problem, let's go ahead and find the pivot point, and let's go ahead and put the pivot right at the end here against the wall here. So I'll put the pivot point right there. and what that does is we can reference all our future torques around that pivot point. Okay, and then we got to draw a free body diagram. Okay, so step number 1, I know this beam weighs 2 kilograms, right? The beam weighs 2 kilograms, so let's put a force of gravity right at the center. So we'll call this Fg. So this is the first force acting on this particular problem. So let's call that Fg1. Okay, so that represents, I guess, like the mass of the beam there. And the raccoon also has mass, so let's draw its force of gravity acting in the downwards direction. We'll call this Fg2. And the basket over here also has weight, so we'll call this Fg3. Now, so we have 3 forces acting in the downwards vertical direction, and it turns out that all of these are perpendicular to the pivot, so that's pretty good. And just like the previous problem, we do have a tension in the rope there, so we'll call that Ft, right? There's a force tension there, so that's your free body diagram. Okay, so we're done with step number 2. Now, step number 3 is we want to find all the perpendicular forces. So we found 3 of them, but we also want to note that for the force in the ropes, the force tension, it actually creates 2 forces, one in the horizontal direction and a vertical force here, which I'll call Fy. Just like the previous problem, we don't really care about the horizontal force, but we want to know what the force in the vertical direction is because that's perpendicular to the pivot point, right? So this is going to equal to the force tension, which is going off at that angle, and this will be sine of 72 degrees. And in this particular problem, we're actually given the force tension, which is 91 newtons, so this will be 91 times sine of 72 degrees. So very similar to the kind of problems that you had in terms of finding the horizontal and vertical velocities for projectile theory. Same idea there. Okay, so since we've found all our perpendicular forces, we want to note that there's a torque over here on our first Fg1. There's another torque over here. There's a third torque over there, and at this vertical force, there's another torque as well. So there's 4 torques that we need to consider in this particular problem. So that establishes everything that we need for step 3. And then finally, we want to use the constant for rotational equilibrium, meaning the object is not moving because all the torques are balanced. Okay, so now let's move on to actually solving the problem now. And just like the previous problem, I'll start off by saying at the pivot, we want to say that the sum of the torques is equal to 0, and that means the object or the whole beam is not moving, and that's because the sum of the torques clockwise is equal to the sum of the torques counterclockwise. Whoops, I'll say, sorry, I usually say clockwise here and then counterclockwise there. Okay, so what does this all really mean? All right, let's go ahead and draw another horizontal line here, and let's just see if we can put this together now. So here's a horizontal line, and we did establish that at the very end here, here's your pivot. And I believe we had a torque in the middle there, and then we had a torque because of the raccoon. We had a torque because of the basket, and we also had a torque here, and that's because of that vertical force. All right, so these are all the perpendicular torques. Okay, so if I'm referencing everything around the pivot point right here, then this torque, the second torque here is going in the clockwise direction. Same with this first torque, and this third torque is also going the clockwise direction. Therefore, this fourth torque is going in the counterclockwise direction. All right, so it's good to maybe draw a little reference diagram to remind yourself where in terms of which direction the torques are going. So if I look at the clockwise direction, there's really 3 torques, right? So torque 1 plus torque 2 plus torque 3. And then on the counterclockwise direction, there's only 1 torque, so we'll label that as the 4th torque. Okay, so the general formula for a torque is force times the distance plus a force times the distance. And then this is also going to be a force times the distance. And this is also a force times the distance. Now, all the forces and distances will be different here, but I just wanted to have the general formula first. And let's go ahead and start seeing if we can plug in some numbers here. Okay, so let's go ahead and take a look at this first torque here, which is denoted over here. Okay, so the force there is really, the force of gravity here is really the mass times the acceleration due to gravity, right? And this is the mass of the actual beam, right? So if I go back to the particular problem, this whole beam weighs 2 kilograms, right? So that'd be 2 times 9.80. Okay, so this force right here is mass times the acceleration due to gravity, and the mass of the beam is 2 kilograms. The acceleration due to gravity is 9.80. And what about the distance? What is this particular distance of this first torque to that pivot point? Well, the force of gravity that's at the center of gravity is always halfway to the pivot point, right? So if the entire beam is 2.2 meters, then this distance has to be 1.1. So I'll times that by 1.1. Plus, now I need the mass of the raccoon. The mass of the raccoon is 8, and it is actually, the acceleration due to gravity is still 9.80, and its distance, right? The distance we don't know, so we'll label the distance as x, all right? So this distance right here is going to be x meters from the pivot point. And what about this third torque here, right? So the third torque. Well, that's going to be plus mass times the acceleration due to gravity. And for this torque right here, the mass of the picnic basket was 1.3 kilograms. Acceleration due to gravity is 9.80. And this particular object is actually the full 2.2 meters away from the pivot point. Right? So a lot of work right there just to establish the clockwise direction there. And finally, we can now go on to the counterclockwise direction, which is this side right there. And we established that this fourth torque right here is really force times the distance. And the force that we said was the vertical force, and that was really Fy. It is the vertical force, but the vertical force we established was, I believe, was 91 times sine of 37 degrees. So that represents the force, and the distance here is going to be roughly, is also going to be 2.2 meters away from the pivot. Okay, so let's just transfer that down here. So 91 times sine of 37 degrees times 2.2 meters away from the pivot. Okay, so a lot of information right there, and now we got to really just go to our calculators here to kind of finish off the rest of the problem here. So if I had to kind of zoom in here and start calculating these numbers here, so this times that is going to be 21.56 plus, and then if I multiply these two numbers together, 8 times 9.80, that's going to be about 78.4x plus, and then we have this third torque expression right here. If I multiply all those three numbers together, that should be roughly 28.028. And then on the right hand side, if I multiply all of this together, we should get roughly 190.4015. Okay, and now we have a linear equation here, and your goal is to find this value of x there. So that value of x is going to be 1.7960 meters, and if you want to round that to 2 sig figures, 1.80 meters is totally fine. Okay, so if I go back to the original diagram right here, what we're saying here is, there's a lot of colors here. What we're saying is that this raccoon can go a maximum distance of 1.80 meters from that pivot point. And if it goes any further than that, then this whole beam will probably break apart and it's no longer in rotational equilibrium. So the maximum distance that this raccoon can walk out is 1.80 meters. Here's a final problem to conclude this video guide. So we want to determine the sum of the torques around the point P, and this point P is like your pivot right there, for the two forces shown below acting on the very light wooden beam, and we need to ignore the weight of the beam. Okay, so this question is slightly different from the two previous questions, but it gives us an opportunity to once again find the perpendicular forces and just set up a general torque expression here. So this force right here in the 20 newtons down here, it's perpendicular to this pivot point, right? So if I want to calculate this torque right here, and I do want to note that this torque looks like it's going in the clockwise direction, right? So if I want to find this torque here, I'll call this torque 1, Any torque can be calculated by the force perpendicular times the distance. And the force in this case is going to be 20 newtons, and that 20 newtons is already in the perpendicular direction, and the distance from the pivot point is 3. All right, so 20 times 3 is going to be 60, so 60 Newton meters. That is the first torque. Okay, and then we have a force that's acting in this angular direction, so that creates two components there, one in the vertical direction and one in the horizontal direction. Now the horizontal direction we're not really concerned with, but we need to find the force in the vertical direction. So if I want to find this second torque, I want to say that this torque is now going in the counterclockwise direction. That can be found by the force in the vertical direction times this distance. And in order to calculate the vertical force, we've done this twice already. So since we have the 10 newtons, it's going to be 10 times sine of 30 degrees, and then we multiply that by the distance to the pivot, and this distance to the pivot is going to be 5. Okay, so if I multiply those numbers out there, that should give me an answer of 25 Newton meters. Now, one thing that I just didn't really, I forgot to kind of note that this is going in the counterclockwise direction, and this is going in the clockwise direction, because remember, torque is a vector, right? So we need magnitude and direction there. Now this question wants to know the sum of the torques. All right, the sum of the torques. So what this really means is we're just adding torque 1 plus the second torque. All right, so this question, the instructions are a little bit different. It's asking for the sum of the torques. So we add the 60, and then I'm actually going to subtract the 25. And the reason why I'm subtracting the 25 is because it's going in the opposite direction, right? So if we're going the opposite direction, let's just go ahead and subtract that. So 60 minus 25 is going to be 35 Newton meters. And since 60 is bigger than 25, it's going in the clockwise direction there. All right, so that is the sum of the torques for this particular problem. In this question, I guess the beam is not in rotational equilibrium. It will definitely move in the clockwise direction. And that's probably because we were told to ignore some other kind of torques that could be in the problem. But this just wanted to see if you can calculate some torques and see if you can get the right direction there. Okay, so there is your answer for this particular problem.